Very nice to meet you all here. I was very honored to be invited by the AI talk. So my name is Guang Yin. I work as an associate professor at the IMBM. So my research field covers the flow structure interaction, hydrodynamics analysis in ocean engineering and offshore technology. So today I'm going to give a brief introduction about how to synergize how to combine the machine learning, which is a very hot modern technology, with ocean engineering. And we focus on the FSI problem, which is fluid structure interaction problems. So we are going to see what is the trend, what is the overview, and what is the future development of how to combine machine learning, deep learning, many technology with the FSI research. How does these kind of technology apply to this research field? So first, a very brief introduction about what is FSI and why we want to do FSI in ocean engineering. So FSI, which is a short name for fluid structure interaction, so very general name. It is a very, we say, you can see it everywhere in ocean engineering. So just to give you several very typical example of a FSI system. For example, the floating wind turbine, which is subject to both the fluids from the wind and ocean waves and currents. And then we have subsea pipelines, which is installed in the subsea environment. And then because it's flexible, when you have a flow coming, it is also under vibration, under the interact with the waves and currents. And we also have a propeller. We also have ROV, underwater vehicle. It is all under the interaction of FSI, flow structure interaction. And then we have also the fish cage. And you have many sort of this kind of a structure, which is both under the interaction with the wind, waves, and currents. So they are response. So what is the focus of FSI is to investigate what is the response of the structure under the interaction with the ocean waves, winds, and currents. And then also the FSI, why it is important, because we all talk about the renewable energy, right? Wind energy, tidal energy, waves energy. But the key idea of the FSI in this sort of question is how to harnessing the energy from the flow induced structural responses, how to harnessing energy from the fluids. So it is also through the interaction between the structure and the fluids. So FSI is the key idea. And then, but investigation of FSI is a very complicated problem because it involved a complex interaction between the solid structure and the fluids. So this happened within the constant matter. So this one is very complicated. You have a nonlinear coupling between the structure and the fluids. So investigate the phenomenon to predict the phenomenon, how to control the system is very complicated. That's why we want to developing advanced technology to achieve these goals. So let's just move back to see what is the traditional approach to investigate such a phenomenon. Because myself, I do the computational fluid dynamics, CFD. I didn't do any experiments, so I just give a very brief introduction of what is the role of computational fluid dynamics in this research. So normally we have a physical problem. So let's say our physical problem is just investigate fluid structure interaction, and then we want to briefly generalize it into a mathematical problem. So we have a mathematical interpretation of this problem. So any problem, any physical problem, if you want to investigate this one, we want to have a mathematical interpretation. So the way to interpret it in the mathematical way is to form this problem into we call governing PDE, partial differential equation. We always generalize everything, physical problem, into a partial differential equation. And when we solve this equation, we can get the solution. So this solution could be what is the fluid's velocity, what is the pressure, what is the structured responses of the immersed structure. So this is the solution. We all get this prediction of the everything through solving the partial differential equation. This is the traditional way. But we know that the partial differential equation is very difficult to solve, correct? So we want to using computational way. We want to using modeling way to solve this equation. So how to solve it? So this equation is very complicated. It could be, for example, this is a typical Navier-Stokes equation governing the fluid structure, governing the fluid motion. And then we have the structural response equation, which has contained many degrees of freedom. I just generalize it into a vector form. So this one, the structural response is under the action of the fluids. So the fluids, they have forces acting on the structure, and the structure, they have a response. So this response can be written as a series of partial differential equation. And then how to using computational way to solve it? We need to build, we call this computational grids. So we have a very large domain. In order to solve this equation, we need to discretize this domain into different grids or meshes. And then within each meshes, we're developing a mathematical approximation to approximate the spatial and temporal derivatives. And then we form this partial differential equation, okay, discretization, and we form a ordinary differential equation, which in the form of we call this a dynamical system. And then we further discretize into a temporal derivative, so we get a very large algebra equation. And then we solve it in the algebra equation, we can get the solution of the partial differential equation. That is the general overview of the traditional method. Almost every CFD software achieving this process. So, but the thing is, if you want to get the solution, we need a very large number of computational grids to achieve this goal, so that the system of this equation can be very large. So we call this the computational. So if you want to achieve a high fidelity computational method, and also the couple with the structure solvers, you need the high cost of a very long CPU hours. And then you also need a very large, we call this the memory, to save this data in order to know the information of the fluids and the structural responses. So the computational cost is very large. And then why is that? So we have a different level of computational. So it could be a low fidelity all the way to the high fidelity. We call this a direct numerical simulation. So low fidelity numerical simulation, we call this a RANS, Reynolds average. So it's just solving a large scale motion. And then in order to achieving a higher and higher the accuracy in the prediction, in the simulation, we need a higher number of computational grids. So that the computational cost is very large, and then you also need a very long time to carry out the simulation. So but it costs a lot of time. But in the reality, we always need a fast solution. So there's a growing demand of efficient understanding, prediction, and control tools to the FSI system. And then for the FSI system is that it is also a parametric. So which means that the partial differential equation, if you change a certain parameter in the equations, the solution can be changed. And then this also corresponding to the reality that if we change a little bit of the parameter, the whole system, the behavior, both the spatial temporal pattern, the dynamical behavior of this system could change with just slight change in the parameter. So we call this problem is a parametric problem. So for example, you can see this is what research we have done. Very simple, it's just the flow past a flat plate. This is a very simple question. But the flow behavior can be very complicated. So normally for a fluid dynamics problem, the governing parameter is we call the Reynolds number. It's just to denote the viscosity property of the fluids. So you can see that within a very little change in the Reynolds number, the flow behavior is changed a lot. So this one we're using a direct numerical simulation to solve this, the fluids. So you can see that if the Reynolds number is very low, the overall flow is very, very simple, very organized. But if the slight change in the Reynolds number, you can see the flow past the simple plate, the overall flow becomes very chaotic, very unorganized. And then you have a very fine, we call this a flow vertical structure, coherent structure, so it can be very complicated. So this problem is very parametric. And then I can tell you that within just One case is you're gonna need a very long time of simulation, but in reality, the overall the flow condition can be changed, constantly changed. So how to predict the flow? How to predict the flow in a very fast way? How to achieve a fast estimation, prediction, and also achieving an efficient solution can be very challenging. So that's why we need the modern technology like machine learning. So how will machine learning achieve these goals? How machine learning help us to understand the flow behavior, to achieving the fast dynamics prediction, how to achieve prediction. Yeah, that's the future trend. Okay, so just give you a very brief view of what is machine learning. So machine learning in general, we can say machine learning is just learn the relationship between the inputs and outputs. So for example, your outputs is what we want to learn from the system. You want to learn the flow pattern. You want to learn the flow velocity. You want to learn the structural responses. This all could be output. So what is the input? Input can be a huge amount of data. So right now you have we already built a lot of CFD tools. We built a lot of experimental setup. We have a huge data, and then you given a new set of data, new set of input, environmental condition. How to fast predict the output, the structural responses, the flow velocity, the temperature, the pressure, everything. So this is just machine learning. So it's a general. But what is inside? What is the relationship? That's what we want to achieve. And then, so machine learning, as you already learned from the literature, there was two types of machine learning: supervised learning, unsupervised learning. So what is supervised learning? Is that suppose we already know the label data, we already know the output, we already know the input, how to build a relationship, and then you have a new relationship. We know the exact value, and then you compare the label data with the output, predict output, and then achieving the minimum loss of this difference. That is a supervised learning. Unsupervised learning, that we do not know anything about the output data. We just want to learn the pattern, general pattern, without the label, without the true ground truth data. But what can we learn from the pattern? What can we learn from the general trend? That is unsupervised learning. So each categories have a different algorithm, and then there are also a kind of overlapping. There's a many way that both. So we're gonna talk to later. There's a many method that combine both the data and the pattern. Okay, we can say this is a physical law. So there's overlapping. So there's many in this method, but I generalize that I personally see that the overall trend of machine learning can be categorized into four objectives. First is feature detection or dimensionality reduction, and then we will go into the details. So what is the achieving goal of this one? And then there's another one is dynamics prediction. Is that because the FSI system is a typical unsteady system. So how to predict the future evolution, how to predict the future trend, the future pattern, the future dynamics based on the current situation, current states. We call this dynamics prediction. And then upon understanding the feature, upon understanding the general pattern, upon understanding the dynamics, we want to achieve the control. Because sometimes we want to suppress the vibration. We want to suppress the response. Sometimes we want to maximize the response because we want to harnessing the maximum energy. So we need the response to be maximum. How to achieve this goal? So that is called control. We want to control this system. And then there's also another emerging trend is called the physics-informed neural network, PIN. We're gonna discuss in a later what is the PIN, okay? But generally, we can categorize the role of machine learning in FSI into these four types of questions. Okay, first one. What is the feature detection? So feature detection is, although we know the fluids dynamics, the FSI system can be very complicated, but we can see that there's always some large-scale motion. We call this a pattern. General pattern. You can see, although so this one is a typical FSI, it is the flow-induced vibration of the pipeline or power cable under the current flow. So you can see that although the fluid dynamics can be complicated, but we can also see that there's a general pattern, correct? So there's a vorticity, there's we call this a shear layer separation, and then the separated shear layer is rho become a vorticity. And then the vorticity is just convected downstream. So this could be understood as a general pattern, overall pattern, a large scale motion. So this is a large scale motion. And even though you can see that this is in a very large scale, it's just wind with clouds past the island. And then you can also see that although there's many fine motion, but the general pattern is very similar to the flow past the cylinder. So you can share a similar pattern, both in the small size and the large scale. So it's a general pattern. So feature detection is how to capture this pattern. And also, for example, this is a very low Reynolds number. This is in a very large scale. And also, if you want to look in the very high Reynolds number, so this is a flow past the cylinder. It's a very typical FSI problem. But you can see that there's a lot of a very fine structure, correct? Very fine. The flow is very rough. What I mean the flow is very rough is that if you look in the detail, you can see a very small motion, very small motion, okay? But you can see the general pattern is still very large scale. It's very similar to this one. So it means that if we just picture on this, if you do not look into the detail, you will also find the large scale motion. So this could be understood as a pattern, a dominant flow feature, or in the more academic way, we call this one a coherent structure. It's coherency. The flow is very coherency. Okay, and then so I also give you a very good example. This is what I teach in the class. So this is a very simple example. This is just a cold plate and the hot plate. So it looks like it's a model of our atmosphere motion. Suppose, especially in the, let's say in the winter time, so when the ground flow, there's many human activities, so the ground can be very hot, but the air is very cold. So we call this one unstable atmospheric motion. So you can see that if this hot air is rising, the cold air is downwarding, correct? So this is a general motion, correct? Cold air downside motion is sinking, and hot air is floating. But you can see the inside, there's a lot of swell motion. So this flow is not very smooth, right? It is a mixing, constantly mixing. But you can see the general pattern is what? You can see a lot of swirling motion. You do not only see the detail. The detail can be very complicated, but you can see the general form. It's a swirling motion, correct? You can clearly see the trend, swirling motion. A lot of constantly happen, swirling motion. So this is a general feature. This is a dominant feature, is swirling. Vortex. So the general idea of feature detection is to using the machine learning way to extract this motion. So how do you achieve this? So the primary goal of the feature detection is to obtain a low-dimensional manifold of experimental data or simulation results. So previously there was simulation results, but we're going to using a way to capture the dominant feature so that the unimportant feature can be neglected. And then we're just using the dominant feature to reconstruct a few dominant features. We can achieving a reconstruct of the system. So we call this a model. We have a many name for this one. You can be achieving. You can using a dimensionality reduction. You can using the model decomposition analysis. So it is all achieving the same goal, is to achieving a low-dimensional description of the system. Just attract the dominant feature, large-scale feature, or dominant flow structure. It's the similar thing. And then this one is that you can see that this is a dog, correct? But if you have a many fine feature, but in neglected this fine feature, you can just see there's a sketch of it. So the sketch you can see this is a dog. So you just a few line, a few feature, you can already say this is a dog. So flow is the same. This is a flow past a wing. You can see that, okay, so we're just using a few modes, a few very organized, very simple, very organized, very large scale. You can already reconstruct the flow field. You do not want to see the other feature, small scale feature, unimportant feature. Just extract the general trend. So this is the first thing we can achieve through machine learning. And then there's many ways to achieve this. We have a proper orthogonal decomposition, which is also in the in computer vision is called PCA, Principal Component Analysis. And then you have also other name, SVD, singular value decomposition, but they are all achieving the same goal. It's just extract the dominant feature. And then we have done a lot of work on this one. So we have an original flow field, which is very complicated. You save a lot of computational grids and with a very long time, very large number of samples. And then we're using model decomposition and then just using several modes, like 5 modes, you can already achieve the general feature. You can see that we're using 5 modes. The general feature, the vortex shading, the large-scale evolution of the vortex can be reconstructed by using a few modes. So this is feature detection. And then this is from the model decomposition analysis, like a PCA, like a SVD, it is all recognized as a linear decomposition. But we know that in the modern machine learning, there's a lot of a nonlinear method. What is a nonlinear method? Neural network. So neural network can achieving the nonlinear detection of the flow feature. So there's a lot of neural network method, such as multi-layer perceptron, MLP. MLP is just we have input states, and then we using a neural network, so we can build the 2 kind of a neural network, encoder and decoder. So what is the encoder do is you have a large number of data, but we're using a neural network just to map to we call this the latent space. So latent space is just extract the large scale feature of the input data. Okay, so this is called the latent space, which is low dimension. So just using a few feature to represent the complicated input. And then you can using a decoder. Decoder is the same, is usually the similar organization of neural network as encoder, just to go back to the output with the same dimension as input. And then you need to train this neural network. The training is, suppose we have a training data. And then we build the neural network, and then we have an output, and you compare the output data predicted by the neural network with the training data. You can do the minimizing the loss, and then we will know what has happened in the neural network. What is the value of the neural network? So this is a MLP. And then there's also a CNN, convolutional neural network. This is very useful for the let's say we want to process an image. We want to extract the general feature of an image. So this one is much more useful for image processing, because as we say in the flow, it's just image. Correct? You have many grids like pixel data. It's a similar way as a pixel data. And then at each grid, you have a velocity, you have a pressure, you have a temperature, you have many information. It just looks like a picture. So this one is also useful in the fluid dynamics. So you're just using the convolutional neural network, and then you have a different layer of CNN, and then finally you can also achieving a latent space. So latent space, in the nutshell, is just a low dimensional feature of the original data. So this is a very good example of how nonlinear ways to achieving the model decomposition, or we say the feature detection, MLP and CNN. And then you have many variants of the MLP and the CNN. You have a variational CNN. You have the deep, let's say the deep. So this one could be very deep. So this is a deep CNN. And you have many methods. So this is just a general picture. So you have achieving different goals. You can make a variant, make a modification of this neural network based on your requirement. And then, so this is a feature detection, and then achieving the dimensionality reduction. So future prediction. What is a future detection? What is the future dynamics prediction? So suppose we have a flow field, and then we regard this as a different snapshot of a picture. And then we're going to using the different way, for example, the CNN or autoencoder, MLP-based autoencoder. And then we're already achieving the latent space. Suppose we are already achieving the latent space, but we know that the FSI is an unsteady problem, correct? So we have a temporal evolution. So each time step, you can encode this one to a latent space. So the latent space is not only at one time, it could be at a different time. So you form a time series. So in order you have so as long as you have a time series, you want to predict the future evolution. So traditionally, how to predict this one? You form this one into a dynamical system. So this one, dA, dt, so A is a vector, so it could be a latent space. And then you want to form this, we call this a dynamical system. And then you're solving the dynamical system, and then you can predict the future evolution. So this is called dynamics prediction. But the problem is, in reality, we know the physical law, so we can form this dynamical system. Correct? We have the Newton's second law, we have a Navier-Stokes equation, we have a single degree of freedom, so we already know the exact form of the dynamical system. But suppose we do not know this one, because latent space is usually we do not know what is happening in the latent space. What is the governing equation of latent space? How to form this dynamical system? How to form this one, and how to make the future prediction. That's how machine learning can do. So they have many methods to achieving the dynamics prediction. We have a RNN, recurrent neural network. It is specially used for time series prediction. We have a LSTM, long short-term memory neural network. It is also used for, specifically used for, designed for time series, temporal forecasting. And then we have a transformer, which is the foundation of a ChatGPT transformer, correct? Using the attention mechanism to achieving the prediction. And then we have a newly developed SIND method, sparse identification, nonlinear dynamics. But it is all predict the long-term evolution of the system. Suppose we do not know the equation of this one. How to achieve this? It's using the similar way to achieving this goal. So we call this dynamics identification or dynamics prediction. So this is a second application of machine learning. So we have did a lot of work. For example, we want to predict the flow past the cylinder. So a very simple one. But previously we know the equation. But now we suppose we do not know equation. We just have a simulation, the snapshots or experimental data we use as the training data. And we're using the MLP encoder is feature detection. So we achieve the low dimensional way to become a latent space, low dimensional latent space. And then we can using the LSTM. So LSTM is one of the way to specifically for the forecasting, time series forecasting. So we're using this way to forecast the future states. And then we're using the MLP to reconstruct back predict the data. And then we have simulation data we compare with this framework. This is usually achieving the same results. But this is totally, we do not have a simulation. We're just using pure data to achieve the future state prediction. Okay. And then we have other method like transformer. So this is a general framework. But in order to achieve the future detection, there's many other ways. You can using LSTM. You can replacing the LSTM with a transformer. So this is a transformer is just ChatGPT. ChatGPT generally just using transformer. It's achieving the same goal. But it's all so it's just replacing the method. But the goal is the same. We just want to predict the future state. And then they have a different accuracy. This is depend on your research. Okay. And then, so this is a second category of the machine learning. We call this the dynamics prediction and control. So traditionally, control is this way. So you have a feedback control. So for example, so this is a typical example of how to suppress the disturbances in the boundary layer. So you have an airplane, you have a seabed, you have a boundary layer. And then you have a small disturbances. And then if these small disturbances enter into the boundary layer, it will developing into a turbulence. So which the drag force is very large. So there's one goal of flow control is to suppress the disturbances. So traditionally, control method is using we call this a modern linear control system. So the modern linear control system, so we have a linear system. And then we know the governing equation of the small disturbances. And then we can design a controller and have a feedback. You sense, you have a sensor to measure how the disturbances, and then you based on the measurement, we have a common filter. You can estimate the states and then design a control way. You have a different control way. You have an actuator to exert external forces to suppress the disturbances, so that you can achieving the control. But the thing is that this system, you already know the system, the linear. We call this a linear system. You already know the system. You already know the differential equation to governing the disturbances. But in reality, suppose we do not know the system. We are totally in the black box. How to achieve this? So this is what we call the reinforcement learning. So when reinforcement learning is very hot topics in the control system, is that we totally do not know the equation. We do not know how what is the governing equation of the system, how to achieve the control. It's by interacts with the environment. So we have suppose we only have some measurement, sparse measurement. We just measure a few spots, a few points in the flow field. And then because the flow field interact with the environments, okay? So we interact this one, and then we build, we call this an agent. So the agent is a neural network. It's usually using a neural network. And then we're using this neural network. It's purely data driven. So we have a measurement, and then we train this neural network to come out with the action. So the action is a control signal. It's a generalized form of a control signal. And then we have using this neural network to come up with the action and then input into the system. So the system will have a response, correct? So we call this response as a reward. This is the outcome of the control, how to evaluate if the control is effective. And then this reward is feeding back to this neural network. So this constantly interact with each other so that the neural network can be updated and then come up with efficient control action to the system. So this is reinforcement learning. So it's constantly interact between the agent and the system and come up with effective learning outcome. So this is a reinforcement learning. It's used machine learning to achieve this way. So you have we have already like in many applications, for example, the control of the flow, the turbulence control to suppress the disturbances. And then we have also the control of the flow past the blood body. So you have traditionally, if you have a unsteady vortex shedding, and then you design this neural network so that the vortex shedding can be suppressed. So we have many this application. Okay, so this is a third one, how to using the machine learning in control. And then PIN, physics-informed neural network, is a new trend. So what is a PIN? So traditionally, we want to solve in the partial differential equation. We're using the numerical way, correct? We're using the approximation to, we're using the finite difference method. We're using the finite volume method to approximate the derivatives. But PIN is that we're using neural network to solve the PDE. So neural network is just from the input to the output, correct? But PDE, what do we get? So solving PDE, we have a temporal, spatial coordinates. We have a temporal coordinates. This could be as the input. What is the output? Output is just the solution of the PDE. For example, if we're solving the fluid dynamics, the flow velocity, the pressure, the structural response, this is our solution. And then we're using the PDE to solve the solution. Or we're using neural network to solve the solution. But what is the neural network? How to build a neural network? We just minimize the loss. So the ping method, the general idea of the ping method is solving the residue of the PDE. So this is a general form of PDE. And then if we have the output, we can inject into the PDE, and then you can see what is the residue of the PDE. So how to update the neural network, we just based on the standard to minimize the residue, to minimize the boundary condition, so that the neural network can be updated. And finally, we can using the updated one to achieving the goal. We have a coordinates, and then we have the solution. So this is a general idea of ping. But the good thing about the ping is that it is combined with the data, measurement data. So we can just enrich the loss. So the pure PDE is just like the residue is minimal. The loss is just the residue of the PDE. But if we have a measurement data, we can enrich the loss so that the prediction can be more and more accurate. So ping is just a combination of supervised learning and unsupervised learning. So suppose we have a measurement data, especially in experiments, we have a lot of measurement data. We can use that. And then you don't need to have a mesh. You just have a point. Suppose we have a special point. We have a town, and then use that as input, and then we can quickly get output. So this is the ping. And then we have also did a lot of work using ping to achieving the prediction of the flow of the vortex shedding, and also the VIV, the vortex-induced vibration. And then this is the ping solution. This is the numerical simulation. So you can see that they look very similar. So the general feature can be captured. And then for the ping, we're just using a very sparse data. So in reality, if you do numerical simulation data, you have a lot of grid points. But this one, so this is the time, this is space. Very sparse data. We can already achieve the reconstruct of the entire flow field and then the structural response. So that is the application of ping. And then, after I talked so many applications, what is still missing in this field? That is how I want to develop over the future several years. I want to achieving several goals. But there's a lot of application, very successful application of machine learning in the traditional numerical simulation or experiments. But most ML, the machine learning application is generally confined to model study. What is a model study? You're just solving very simple PDE. So many people, they want to test if their machine learning application is feasible. They test it on the ML simple PDE. But in reality, the flow can be very complicated. You have we saw this multi-scale feature, very chaotic feature, unsteady feature, and then you also combine with the structured responses can be more complicated. But how to transform the simple model problem, model PDE, to a complicated problem is still very challenging. But we want to achieve this goal. And then the second one is, so this one you are solving a large-scale simulation. But in reality, we do not have so many computational power. We only have a sparse measurement. We call it a sparse measurement is that we have a limited data to the system. How do we achieve the prediction? How do we achieve the feature detection using very limited data? So I'm using the parabolic analogy. This is just look like a blind people want to know the elephant. So the elephant is very large. We call this the FSI. It's just the elephant. Very large, very complicated, but we only have a limited access to this system. So it's just blind people. We know nothing about the entire system. We can only touch a part of it. So just a part of the information is, we call this a sparse measurement. But the blind people with the elephant is that you only know, so you have a misunderstanding of the system, correct? So they have a wrong guess of the elephant. But what I want to achieve is that with only this sparse measurement, but we still have very accurate information of the entire system. Only touch part of it, we know, oh, this is an elephant. This is not the other things. How do you achieve this goal? So this is our future trend. What do we want to achieve this goal? So it's challenging. So very challenging work, very promising. We still have many ongoing work. So if you have interest, we can build a collaboration to achieving this challenge. Okay, so if you have any questions, you can ask me. Okay, thank you very much. Yeah.